Hello, people. This is section 3.10 from Calculus Early Transcendentals, James Stewart, 8th edition, and we are talking about linear approximations and differentials. So what is the central idea in first semester calculus? The biggest issue or the biggest concept is the equation of the tangent line. And why do we study the equation of the tangent line? Because it's a really nice approximation to the curve for values really close to that point where you're taking that tangent line. All right, and so the linearization of a curve is nothing more than finding the equation of the tangent line. So do not think that it's anything extra special that you need to do. But if you ever are asked, find a linear approximation to the curve of f of x at a value of a, you are finding nothing more than the equation of the tangent line. And so what are those steps? You want to first find the point x equal to a and y equal to f of a, and so that your point x1, y1 is equal to a f of a, right? And step 2, you want to take the derivative of f of x and you want to evaluate at x equal to a, and let's say for instance your curve was defined implicitly, then you could do implicit differentiation and then you might need x and y, but that's okay, you can do that. But your f prime of a is going to be your slope m, and then your equation of your tangent line is going to be y minus y1 equal to m times x minus x1, and if you wanted to use those values, a f of a, y1 is going to be f of a, your slope m is going to be f prime of a, and your x1 is going to be equal to a. So if I were to solve for y, I would get f of a plus f prime of a times x minus a, and we do have that is your linear approximation to the curve. It is your equation of the tangent line, and so we can call that our L of x. All right, so if you're ever asked find the linearization or find the linear approximation or find the equation of the tangent line, it means the same thing, and this is your process for doing so. All right, so let's take a closer look at that, and let's take a look at that tangent line. So here in pink, this is your tangent line. All right, and we're just going to take some notation here and just define some of, or just look closer. And if we were to look closer and closer and closer, we can see that if for values really, really close to x, our tangent line actually really does look like our curve, and that's really nice. And so we just want to sit there and look at applications of that. All right, so I'm just going to go ahead and erase those things, but just to bring up some of the notation of delta x and delta y. So just in taking a look at the picture here, if I were to start at x and I were to go to x plus delta x, if I went over this distance here would be delta x, right? And if I went up a distance of y along my tangent line, knowing that my tangent line's slope is going to equal dy dx, then I know my dx here on my tangent line, if I'm going to stay there, my dx is going to be this distance as well, but this distance here is going to be dy, right? But knowing that the dy dx is going to be the limit as delta x approaches 0 of delta y over delta x. And what is our delta y? Our delta y is the actual change in function values, and that's going to be f of delta x plus, or f of x plus delta x minus f of x, and then that would be x plus delta x minus x. That's the change in x, and we would just have delta x on the bottom. So we do see that your dy does equal delta x, but your delta y, not your dy, is just going to be the actual difference in function values, right? So our function values would be here and here, because those would be on the curve of f of x, right? And so we would have that this distance here would just be delta y, right? But as the values of x, or as delta x goes to 0, then we would actually come upon the slope of the tangent line. Good? All right. So we see, as we do zoom in closer and closer to our value of x, that the distance between delta y and dy becomes smaller and smaller and smaller. So as delta x goes to 0, our dy kind of approaches our delta y, right? Good. So we want to use that idea. Good. So I just want to point out some of those definitions. All right. So again, dy dx is going to equal the limit as delta x goes to 0 of delta y over delta x. Some of the definitions of our values here just from that picture. We have that the dx will always equal delta x. We know that our delta y is the actual difference in function outputs. All right. And we define, just using dy dx equal to f prime of x, just multiplying on both sides by dx, by that differential dx, we have that dy here is equal to f prime of x dx. And so for values super close to x, or in other words, as delta x approaches 0, we can approximate or say that delta y is approximately equal to dy. So in other words, our f of x plus delta x minus our f of x is approximately equal to f prime of x dx. So if I were to just use that equation as an estimate, and whatever I want to calculate would be my f of x plus delta x, I can say that my f of x plus delta x would be approximately equal to f of x plus f prime of x dx. Or in replacing our dx with delta x, we can say that our f of x plus delta x is approximately equal to f of x times f prime of x times delta x. And I know that's a lot to handle, but we can use this type of scenario to make some estimates of things, and then we can also use that to, if we've got functions where we can easily calculate some values of f of x of some values, but we can't necessarily do it with other ones, we can use differentials. Good. So we can also talk about maximum errors and relative errors and percent errors with differentials as well. So just wanted to point those out. And so let's just do some. All right. So let's say, for instance, we want to use the linear approximation to estimate. Let's estimate 3.9. The square root of 3.9 using differentials. So we're just going to use this one instead of 4.2. All right. So I know that I can easily calculate the square root of 4, because this 4 is a perfect square, but 3.9 is not a perfect square. But if I want to say that my f of x plus delta x is going to be my f of 3.9, right? Where my f of x is going to equal the square root of x, right? I can really write this as the square root of 3.9 does equal the square root of 4 plus minus 0.1, right? And if that is my x plus delta x, I can see that my x here is going to be 4 because that 3.9 is really close to 4. So we always want to pick something that we can easily calculate. All right. So I know that my square root, or my f of x plus delta x, is roughly going to equal f of x plus f prime of x delta x. I can see here I'm going to need the derivative of the square root of x. So what is the derivative of the square root of x? The derivative is 1/2 times x to the minus 1/2, which is equal to 1 over 2 root x. So I can see here that my square root of 3.9 is roughly going to equal the square root of 4 plus 1 over 2 times the square root of 4 times my delta x. And my delta x here is going to be negative 0.1. That makes sense? All right. So what does that equal? Square root of 4 equals 2. And 1 over 2 times the square root of 4 is going to be 1 over 4, right? And 1 over 4 times 0.1, or negative 0.1, is going to be negative 0.1 over 4. And that, upon using a calculator, is roughly going to equal 1.975. Good. So if you ever want to make an approximation, you could do a fourth root, right? A fourth root of 16 or a fourth root of 17, right? If we wanted to do a fourth root of 17, we would say that that's equal to the fourth root of 16 plus 1, and that's going to equal our x plus delta x, and we would want to use our f of x to be the fourth root of x. So we'd want to calculate our f prime of x, right? And so we would just say that the fourth root of 17 is approximately equal to the fourth root of 16 plus the derivative with respect to x of the fourth root of x, but evaluated at x equal to 16, but then times that 1, which is that delta x. Make sense? So that's how you could approximate functions using values using differentials. All right. So how would I calculate my maximum error and my relative error and percent error, and what do those mean? All right. So if we are using our maximum error is going to be defined to be the dy. And our dy, remember, is equal to f prime of x dx. So in this case, for the case of 3.9, we're using the square root of x. So this is going to be 1 over the square root of 2x times dx at x equal to 4 and delta x equal to minus 0.1. So we would say this is 1 over 4 times negative 0.1, and we're going to get negative 0.025. That's going to be our maximum error. So what is relative error? Relative error is going to be the max error over the exact value, right? And so in this case, it's going to be 0.025, or negative 0.025, over the square root of 4, because we were using the exact value of that square root of 4. So we're going to get minus 0.025 divided by 2, and that's going to give us a 0.0125. Our percent error is going to be our relative error as a percent. And so that's just going to give us a 1.25%. And that's how much we would be off by, which is not too bad. All right. So moving forward, let's just go over some scenarios here where we would know how to set up that approximation of evaluation. So here, if I wanted to calculate the fourth root of 19, 19 is really close to 16, which is easy to find the fourth root of, which is 2. So since the fourth root of 16 is an easily computable value closest to the fourth root of 19, we would approximate using the linearization of what function. We'd use the fourth root of x, because that is what our at the value of x equal to 16, because we're trying to compute the one at 19, and 19 is relatively close to 16. And then we would deduce that the fourth root of 19 is approximately equal to f of 16 plus f prime of 16 times delta x, when delta x here would be 3, right? Because 19 is 16 plus 3. That makes sense? And our 3 would be delta x. And this is our f of x plus f prime of x at 16. All right, so again, e to the 0.04. I'm sitting there going, okay, I can evaluate e to the first power very easily, and I can evaluate e to the 0 very easily. Which one is closer to e to the 0.4? I think 0.4 is closer to 0 than 1. So I'm going to say since e to the 0 is an easily computable value closest to e to the 0.4, then we can approximate e to the 0.4 using the linearization or the linear approximation of e to the x at 0, right? And deduce that e to the 0.4 is roughly equal to e to the 0 plus the derivative at e to the 0, which would be e to the 0, times the differential and the difference, and the difference here being 0.4. Good? That would be our delta x. Since a sine of 0.1 is really, really close to sine of 0, right? So since sine of 0 is an easily computable value closest to sine of 0.1 with delta x equal to 0.1, we can approximate sine of 0.1 using the linearization of sine x at x equal to 0, and deduce that sine of 0.1 is roughly equal to sine 0 plus the derivative of sine evaluated at 0, and the derivative of sine evaluated at 0 is cosine 0, but then we would be multiplying by delta x, right? Because that's our delta x would be 0.1. Make sense? All right. Which is going to be equal to 0.1, pretty much. All right. So I think you get the idea. So again, cosine of 181 is very close to cosine of 180. So since cosine of 180 degrees is easily computable value closest to cosine of 181, we can approximate the cosine of 181 using the linearization of cosine x at 180 degrees, and deduce that the cosine of 181 is approximately equal to cosine of 180 degrees plus the derivative evaluated at 180, and the derivative of cosine is minus sine, and then times the differential, and the differential would be 1 degree. Good, and that would be our delta x. All right, so hopefully you get the idea of how to set those problems up. All right, so let's take a look at some evaluations here. And this is just an application of the dy is a differential and the dx is also a differential. All right, and what is dy? dy is f prime of x dx, and the differential dx does equal delta x. So just in this scenario, we want to just use a pictorial application, and it's very similar to one here. Good. So, in looking at this, it says graph y and determine dy, or just b. Find dy at x equal to 1 if delta x is equal to 0.5. Illustrate your answer on the graph in A. So what is your dy? Your dy is f prime of x dx, and we see here that x, or y, is equal to x squared. So what is the derivative? 2x, and then we multiply by dx. And if we're going to evaluate at x equal to 1 and delta x equal to 0.5, we end up with 2 times 1 times 0.5, and that will give us 1. So what is my dy if I go over in pink here at 1, and if I go up at x equal to 1, if I go over by 0.5, I get to here. And then if I go up 1 from that point, from that value at x equal to 1, my function value is here. And if I go over 0.5 and then up dy, up a value of 1, I'm going to get this point here. Good? And that would be my dy. And, my dy would actually be in pink. Sorry. So I would have dy. And what is my delta y? I would actually be taking I do have that in dy. My dy is actually going to be, I have this as it's actually incorrect. The dy would actually be in blue. Good. So I do have it. I had it right the first time. My dy would actually be in blue because I'm only going up by 1. So from here to here is just 1. But if I do my delta y is my actual change in function output. So I'm going to do f of 1 plus 0.5, take away f of 1, and my function is y equal to x squared. And so 1.5 squared is 2.25. And f of 1 is 1 squared, and that is just 1. And if I take my difference there, I get 1.25. So my delta y is actually going to be the one in pink, right? And that is going to be my difference in value there. All right. So moving some practical evaluations here. Practical applications of your differential. It says the diameter of a sphere is approximated to be 20 plus or minus 0.1 centimeters. Using differentials, estimate the maximum error, the relative error, and the percent error in calculating that volume. Okay, so our maximum error is going to be dV. Okay, and so if we know our volume here is going to be the volume of a sphere. And the volume of a sphere is 4/3 pi r cubed. So my dV dr is going to be 4/3 times pi times 3r squared, right? Or 4 pi r squared. So my dV is going to be 4 pi r squared times dr. And what is my dr? My dr is going to be 0.1. Good. And my r is going to be 20. So if I plug those values in, my maximum error is going to be 4 times pi times 20 squared times 0.1. And 20 times 20 is 400. 400 times 4 is 1600. And 1600 times 0.1 is going to be 160 pi. Good. That is my dV. That is my maximum error in approximating the volume using just 20 and not 0.1. All right, so what is my relative error? My relative error is going to be my maximum error divided by my volume, my total one. So it's going to be, if I have my dV is going to be 4 pi r squared times dr, and my volume is going to be 4/3 pi r cubed. I know I can cancel some things. I can cancel 2 r's with 3 r's to leave 1 r. I can cancel a pi with a pi, and I can cancel the 4 with the 4, and I'll have 1/3 left over. And so I end up with 3 times dr over r. That's going to be my relative error, and if I plug in my values here, I'm going to get 3 times 0.1 over 20, and what does that give me? I get 0.3 divided by 20 is going to give me 0.015. That's my relative error. And what is my percent error? My percent error is the relative error as a percent. And so that's just going to give me, I'm just going to be off by 1.5% of the actual measurement of the volume. That's cool, right? That's not so bad. Let's take a look at this question here. It says, the interior of an open cylindrical tank is 12 feet in diameter and 8 feet deep. The bottom is made of copper and the sides made of steel. Use differentials to approximate how many gallons of waterproofing paint are needed to apply a 0.05 inch coat to the steel part inside the tank. All right, note that 1 gallon is 232 cubic inches. All right, so how do we do that? Well, we can use our differentials. And so what is volume of our cylinder? The volume of our cylinder is pi r, the area of the base, times the height. And note that we are actually in feet. Good. And we want to find our dV, right? And what is our dV? Our dV here is going to be, our dV dr is going to be 2 pi r times h. H here would be a constant. So our dV is going to be 2 pi r h times dr. Good. And if we were to plug in when, what is our radius? If our diameter here is 12 feet, our radius is going to be 6 feet. And so we're going to get 2 pi times 6. Our height is 8. And our dr, using, it says 0.0, we're going to use 0.05 as our dr. Right? And that's how much we can approximate, because that's kind of thinking how much we're off by, right? And measuring. So we're just going to sit there and think, what is our differential? And that is going to approximate how much we, the difference in volume, the corresponding, right? Our corresponding change in volume is going to be approximately our dV, right? And this is going to be our volume of paint needed. So just think that we approximated the volume of the interior using 12 feet in diameter, but we're going to be off by 0.05 because we're going to be painting the interior and waterproofing it. So that's the volume of paint needed, and that's why we're going to approximate the volume of paint using dV. Does that make sense? And so we're going to use our dr as 0.05. So what do we get here as our dV? And this is going to be in cubic feet, right? So how do we actually get into cubic inches? Now we're getting into some dimensional analysis. So first, let's just simplify as much as we can here, and we will get 2 times 48 times 0.05, and we're going to get 4.8 pi cubic feet as our dV. That's how much we need, but we're going to try to see how many gallons. What is this in gallons? All right, so we've got dV equal to 4.8 pi cubic feet. If I multiply by 1 foot gives me 12 inches, I'll have to do that 3 times so that I can cancel cubic feet with 3 feet, right? And so that's going to give me my cubic inches. So if I do 4.8 times 12 times 12 times 12, I get 8,294.4 pi cubic inches. And so with my dV equal to 8,294.4 pi cubic inches, how many gallons is that? Well, we know that there are 231 cubic inches in 1 gallon, and we can cancel our cubic inches here, and we're going to get 8,294.4 divided by 231 is going to give me 35.9 pi gallons. And if you want to multiply by pi, then we're going to get approximately 112.8 gallons needed. So hopefully that will help in dealing with differentials, which is kind of nice. Keeping in mind your differential dV is your error, and that does it. All right, so the next chapter or the next section that we're going to cover is